This video is about P block elements of intermediate first year syllabus, that is group 13 and group 14. Group 13 is also known as third year group. Group 14 is also known as fourth year group. Hello everybody. In this video I am going to explain about group 13 boron family and group 14 carbon family. So group 13 is also known as third year group. Group 14 fourth year group. And the elements are relate elements, third year group, so which is boron family. The elements are boron, aluminium, gallium, indium, thallium and nihonium, NH. So fourth year group, which is carbon family, consists of carbon, silicon, germanium, tin, lead and flerovium. So atomic numbers are boron 5, we know. Here 13, 31, 49, 81, 113. Next year 6, silicon 14, 32, 50, 82, 114. These are atomic numbers. So here you have to remember elements and corresponding atomic numbers. Next, about group 13 or third year group. So first point, minerals of boron. Boric acid, H3BO3, very important compound. Next, borax, Na2B4O7 10H2O, very important compound, borax. Next, colemanite, Ca2B6O11 5H2O. Next, general electronic configuration of third year group elements is Ns2Np1. That means 3 valence electrons. Next, here inert pair effect is very important. Boron, aluminium, gallium, indium, thallium. So from here 2 parameters important. In thallium to boron, boron to thallium. So thallium to boron plus 3 oxidation state increases and boron to thallium plus 1 oxidation state increases due to inert pair effect. Due to inert pair effect. Very important. So for top elements higher oxidation state, for bottom elements lower oxidation state is stable. So here it is given inert pair effect. The reluctance of Ns2 electrons to take part in chemical bonding formation is known as inert pair effect. So due to inert pair effect, for lower elements, lower oxidation state is stable. So thallium is more stable in +1 oxidation state. So top to bottom, lower oxidation state stability increases. Next, see here it is given. So due to inert pair effect, +1 oxidation state is highly stable for thallium. So Ns2 electrons will not participate in bonding formation for lower elements. Next, the most common oxidation state of third group elements is +3. So boron to thallium +3 increases. Thallium to boron +3 increases. Boron to thallium. See here, boron to thallium +3 decreases. That means +1 increases. Here remember like this. Next, AlCl3 exists as dimer. We will discuss structure later. AlCl3 dimeric form. Next, Nature of aluminum. Aluminum is amphoteric because that can react with acids as well as bases. Alkalis means bases. Next, aluminum is passive means here inactive towards concentrated HNO3 due to formation of protective oxide layer on the surface of aluminum. So passive means inactiveness. Next, see here compounds in which electron deficient nature of boron compounds. Compounds in which central atom does not have 8 electrons in valence shell are electron deficient compounds. Less than octet of electrons. Examples, boron trihalides and diboron B2H6. We'll discuss later. Next, borax bead test. Very, very important for competitive exams. So, what is borax? Na2B4O710H2O. Borax, first on heating, it loses 10 water molecules to form just borax. Anhydrous form of borax, Na2B4O7, which on strong heating can release NaBO2, sodium metaborate and boric anhydride. So this gives glassy mass or glassy bead. So this mixture can react with transition element oxides to form or to give characteristic colors. So therefore, borax bead test is useful for detection of transition metals, transition metal ions. See here, example is given. So B2O3, here active species is B2O3, boric anhydride, that reacts with transition metal oxides to form corresponding metaborates, which are having characteristic color. So based on color, we can identify which transition metal ion is present. Cobalt can form blue colored bead, blue color, which is metaborate. Next, about boric acid, H3BO3 or BOH thrice. In any way you can write. So it is weak monobasic acid. How it is? Acid means when a boric acid BOH thrice, it is having one vacant orbital that reacts with water. In water we have two types of ions, H plus and OH minus. Boron attracts OH minus and it forms BOH 4 times minus with release of H plus. So boric acid is accepting hydroxyl ion from water and releases H plus. So since it is accepting only one OH minus, it is monobasic acid. And obviously it releases only one H plus. So one molecule of boric acid can release one H plus. Therefore it is monobasic acid. So this is not protonic acid. Remember that. It is not protonic acid. Protonic acid means the compound which can release H plus ions directly. But here this compound is not releasing H plus ions directly. It is accepting OH minus from water and releases H plus ions from water. It is not directly releasing H plus. Therefore, not protonic acid, indirect acid. Next. So, boric acid is layer-like structure which are joined by, that means BO3, 3 minus units are joined by hydrogen bonds. So simply remember, structure of boric acid is polymeric due to hydrogen bonds. Next, boric acid on heating forms first metaboric acid HbO2, which on strong heating gives boric anhydride or boric oxide. Boric anhydride anhydride or boric acid. So boric acid on heating, first it gives metaboric acid, which on strong heating gives boric anhydride. Next, about diborane. So structure of diborane, very very important. So B2H6. Let's explain structure. First preparations. We will see preparations after that structure. So preparations. BF3, boron trifluoride, reacts with lithium aluminum hydride to form diborane. Your solvent will be diethyl ether solvent. Next, sodium borohydride plus I2 also gives diborane. Next, BF3 reacts with NaH. NaH means metal hydride, sodium hydride to form diborane. Here we have to remember these equations. Next, properties. It is colorless and highly toxic gas. Toxic means here poisonous. So diborane reacts with water to give boric acid. Very very important reaction. With release of H2. Next, diborane reacts with carbon monoxide to form boron carbonyl addition compound. Next, diborane reacts with triethylamine to give borazine adduct. Adduct means here addition compound. Addition compound. So diborane structure will be like this. B2H6. So this hydrogen one is above the plane and other one below the plane. Remember like this. So here boron atom undergoes sp3 hybridization. Here also sp3. Next. So diborane, next property, reacts with ammonia at 120. 120 means here take it as low temperature to form diammoniate of diborane. Diammoniate of diborane at low temperatures. Next, which on heating at 200 gives borazole or borazine or inorganic benzene. See here B2H6 NH3 low temperature gives addition compound diammoniate of diborane. 2 molecules of ammonia will be attached to 1 mole of diborane, which on strong heating gives B3N3H6, which is inorganic benzene or borazole or borazine. Very very important. With release of H2. Here remember moles also. Moles. So here ammonia molecules can be 6. It should be 6. 6 molecules of ammonia. Next. The formula of borazine is B3N3H6. It is also known as borazole or inorganic benzene. Inorganic benzene. Next. In B3N3H6, I will write structure. B3N3H6 will be like this. Here one hydrogen. Structure will be similar to that of benzene. Next. So on each boron, there is one vacant orbital. Vacant orbital, but under nitrogen, one lone pair. So this will give day 2 bond. Next here lone pair, again one vacant orbital, one day 2 bond. Next here also one lone pair, one vacant orbital, one day 2 bond. So in this structure, boron sp2 and nitrogen also sp2 hybridization. So structure is similar to that of benzene. Therefore, it is inorganic benzene. Nitrogen to boron day 2 bond formation. Next. So boron and nitrogen sp2 hybridization. Next, borosine on strong heating gives boron nitride. It will be also known as inorganic graphite. Boron nitride, which is harder than diamond. Next, in diborane, each boron atom undergoes sp3 hybridization. So I will explain structure. Yes, structure will be like this. Boron atom undergoes sp3 hybridization. Each boron sp3. sp3 means we know 4 hybrid orbitals. So all are sp3, sp3. Here also sp3. So structure is very important. So many questions will be there on this structure. See, one unpaired, 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 and this is vacant. Next here also unpaired, 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 and it will be vacant. Next, see here 4 hydrogen atoms will form bonds with 2 boron atoms. 4 hydrogen atoms in this way. Next, 2 hydrogen atoms will form different bonds. Here one unpaired, here also one unpaired hydrogen. So here important point is, here these 3 will combine to form a new type of bond. Like this. So 3 atoms sharing 2 electrons. That means here 3 centered 2 electron bond. Next remaining are 2 centered 2 electron bonds. 2 centered 2 electron, 2 electron. So very important. So this is actual structure of diborane. Next, see here. 3 centered 2 electron bonds, 2. And 2 centered 2 electron bonds, 4 are present. Which is very important for competitive exams. 3 centered 2 electron bonds means 3 atoms sharing 2 electrons. 2 centered 2 electron bonds means 2 atoms sharing 2 electrons. Next, simply we can write like this. Boron and boron. Here 4 hydrogens. Next, here one more hydrogen. One hydrogen above the plane and other will be below the plane. This is the structure, simple structure. So this BH2 and this BH2 will be in same plane. These two will be in same plane. So total 6 atoms will be in same plane. 2 BH2 bonds. BH2, BH2 lies in same plane. Now check the points. Here these are the points. See here, in diboron, each boron atom undergoes sp3 hybridization. So diboron contains 4 terminal hydrogens and 2 bridging hydrogens. Terminal means last. See here, these are terminal hydrogens. 4 terminal and 2 bridging. H, middle bridge. Next, boron atom in diboron bonded to 4 terminal hydrogens, which are sigma sp3 and s bonds, which are 2-centered 2-electron bonds. 2-centered 2-electron bonds. Normal bonds. Next, remaining points. BHB bridging bond is formed by overlapping of sp3 hybrid orbital with 1 electron from one boron atom, 1 s orbital of hydrogen atom and vacant sp3 hybrid orbital of other boron atom to form 3-centered 2-electron bond, which is known as banana bond and toe bond. Very, very important. Half-filled sp3 hybrid orbital of one boron, 1s orbital of hydrogen atom and vacant sp3 hybrid orbital of other boron will combine to form 3-centered 2-electron bond. 3-centered 2-electron bond, which is banana bond or toe bond. Next, in B2H6, 4 terminal hydrogen atoms and 2 boron atoms lie in one plane. Next, remaining 2 hydrogens, one is above and other one is below the plane. Next, lithium borohydrate, sodium borohydrate are reducing agents. These are used in organic chemistry frequently. Next, aluminium forms alloys with copper, manganese, magnesium, silicon and zinc. These are used in utensil making. Utensils and aeroplane transportation industry. So alloys of aluminium are frequently used in aircraft parts preparation, manufacture of aircraft parts. Next, group 14, carbon family. Elements are carbon, silicon, germanium, tin, lead and flerobium also. Flerobium. Next, fourth A group elements are also known as, here now, just carbon family only. Carbon family. Next, general electronic configuration is Ns2 Np2. So here also inert pair effect is there. Carbon, silicon, germanium, tin, lead. In this direction, here common oxidation states are +2 and +4. So in this direction +4 state increases, in this direction +2 due to inert pair effect. Due to inert pair effect. So for lower elements, lower oxidation state is stable. For higher elements, higher oxidation state is stable. Inert pair effect. It is observed in group 13 and group 14 elements. For group 13, plus 1 plus 3 common oxidation states. Here for group 14, plus 2 and plus 4 common oxidation states. For lead, highly stable state is plus 2. Remember that point. Next. So 17th most abundant element by mass in earth crust is carbon. 17th position in earth crust. Next, mineral of tin is cassiterite, SnO2, cassiterite. Mineral of lead is galena, PbS, galena, or cerussite, PbCO3. Next, these are general properties. So first, covalent radius, carbon, silicon, germanium, tin, lead. Down the group, radius increases. Electronegativity, carbon, lead, germanium, tin, silicon. Very, very important. Electronegativity. Next, metallic nature, carbon, silicon, germanium, tin, lead. Down the group increases. Next, ionization energy, carbon, silicon, germanium, lead, tin. This is anomalous pair. This is also important. Next, melting point, carbon, silicon, germanium, lead, tin. Boiling points, carbon, silicon, germanium, tin, lead. In case of melting points, last two elements will be reversed. Next, density, lead, tin, germanium, carbon, silicon. So all these orders are very, very important. Next. So common oxidation state is plus 2 plus 4. Already we have discussed. Carbon to lead plus 2 increases. Lead to carbon plus 4 increases due to inert pair effect. So that is due to inert pair effect. Remember that. So here for lead plus 2 is more stable than plus 4 due to inert pair. NS2 electrons will not participate in bond formation for lead. Therefore only plus 2 is stable. Next, for germanium, Ge plus 4 is more stable than Ge2 plus. For top elements, higher state is highly stable. Next, carbon can form two types of oxides, CO and CO2, monoxide and dioxide. We know this. Next, acidic nature of oxides, CO2, SiO2, GeO2, SnO2, PbO2. Almost tin and lead oxides are amphoteric. Next, reactivity towards water. Carbon, silicon and germanium are not affected by water, but tin decomposes steam. Very, very important. This is a previous MSET question. Tin reacts with steam to form H2 gas. Next, thermal stability of group 14 hydrates. CH4, SiH4, GeH4, SNH4, PbH4 hydrates. Stability that depends on lattice energy. Next, thermal stability of tetrahalides. Your tetra should be there. Tetrahalides. CF4, CCl4, CBr4, Ci4. So due to small size, carbon can accommodate 4 fluorines but not 4 iodines. Iodine very large in size. Therefore, carbon cannot accommodate 4 iodine atoms around it. Therefore, that is highly unstable. Next. So CCl4 does not undergo hydrolysis due to absence of d orbitals in carbon. So while SiCl4 undergoes hydrolysis due to d orbitals. Very, very important. This is also previous question. Next, silicic acid is formed by hydrolysis of SiCl4. H4SiO4. Silicic acid. Next one. Next, tetrahalides of silicon, germanium, tin, lead are Lewis acids due to the availability of d orbitals. Due to d orbitals in valence shell. Next, Pb does not exist. PbI4 does not exist. For Pb, we know +2 oxidation state is highly stable. Pb4 plus unstable due to inert pair effect. Therefore, PbI4 does not exist. Next, here hybridization of central atom in SiF6 2 minus, very very important, sp3d2. Similar in case of germanium hexachloride. Next, so anomalous behavior of carbon is due to small size, high electronegativity, high ionization potential and absence of d orbitals. That means first element properties different from that of rest of the elements due to these following reasons: small size, high electronegativity, high ionization potential and absence of d orbitals in valence shell. Next, catenation. Self-linkage of atoms to form long chains or branches or rings is known as catenation. It is a unique property of carbon. Therefore, it is forming millions of organic compounds. So, order of catenation: carbon highest. Next, silicon, germanium, tin. Lead is not having any catenation property. So, catenation property is due to high bond dissociation energy of carbon-carbon. Allotropy. Allotropy means existence of an element in two or more physical forms having similar chemical properties but different physical properties. Very very important. So for carbon, two types of allotropes are possible: crystalline and amorphous. So crystalline allotropic forms are diamond, graphite and fullerenes. Crystalline. Amorphous forms: gas carbon. One second. Amorphous forms of carbon. Carbon are coke, charcoal, wood charcoal, animal charcoal, lamp black, carbon black and so on. So many will be there. Amorphous forms. Crystalline means having definite geometry. Amorphous means no definite form. Next, hybridization of carbon in diamond is sp3. Sp3 means one carbon atom is bonded to four more carbon atoms like this. Tetrahedral arrangement. And each carbon undergoes sp3 hybridization. In diamond, each carbon is attached to four more carbons tetrahedrally. Next. So hybridization of carbon in graphite and fullerenes is sp2. Next, carbon-carbon bond length in diamond is 1.54 angstrom units. Bond angle sp3 angle 109 degrees 28 minutes. Next, carbon-carbon bond length in graphite is 1.42. Bond angle 120 due to sp2. See, in fullerenes, minimum number of carbon atoms present in 60. That means C60. So simplest fullerene is C60, Buckminster fullerene. So minimum number of carbon atoms in fullerenes is 60. C60 is also known as Buckminster fullerene. Next, compounds of carbon and silicon. So here water gas. It is formed by passing steam over red hot coke. Coke is allotropic form of carbon. C plus steam gives CO plus H2. This is water gas or syngas or synthesis gas or simply blue gas. Next, producer gas. It is formed by passing air over hot coke. C plus O2 plus N2 gives CO plus N2. So water gas is combination of CO and H2. Producer gas is combination of CO and N2. Next, carboxyhemoglobin. It is formed by combination of CO with hemoglobin. It is 300 times more stable than oxyhemoglobin. Therefore, CO is highly poisonous. Next. The crystalline allotropic forms of silica are quartz, tremendite, cristobalite. Amorphous forms are agate, jasper, onyx. So these are important for MSET. These points, these 2 points, very important. Next, purest form of silica is quartz. Next, crushed form of quartz is sand. So these are main points. Next, the mixture of amorphous silica and quartz is called flint glass. Silica is covalent, three-dimensional network solid. Silica means we can draw structure like this. Each silicon is bonded with 4 oxygen atoms, here and so on. Each oxygen is bonded to 2 silicon atoms. Three-dimensional arrangement. So for silicon, coordination number is 4. For oxygen, coordination number is 2. That means simply each silicon is bonded with 4 oxygen atoms. Therefore, coordination number 4. Each oxygen atom is bonded with 2 silicon atoms. Coordination number 2. 3D form. Next. Silica on reaction with carbon forms carborundum. Silicon carbide is also known as carborundum. It is used as abrasive. Abrasive means cutting of metals. For cutting of metals it can be used. Or for polishing of metal surfaces it can be used. Polishing. Next, silicones. These are organosilicon polymers containing SiO-Si linkages. SiO-Si. Hydrolysis of RSiCl3 gives cross-linked silicones. Cross-linked. Here 3 types will be there. 3 types. For silicon polymers, remember R3SiCl, R2SiCl2 and RSiCl3. So first one gives only R3SiCl, just dimer. Next, R2SiCl2 gives chain polymer. RSiCl3 gives 3D polymer. So 3 types of silicones. Silicones will be formed by these 3 types only. Only 1 chlorine atom is present means dimer. 2 Cl atoms, chain silicones. 3 Cl atoms, 3D silicones. Next, silicates. The metal derivatives of silicic acid are silicates. Basic unit is SiO4 4-. Basic unit of silicates. Next, man-made silicates are glass and cement. In these SiO4 4- units will be present. Next, zeolites. Hydrated sodium aluminosilicates are zeolites. Sodium aluminosilicates are zeolites. Next, these are having honeycomb structure. Honeycomb structure we know. Next, these are used as ion exchange materials or as molecular sieves. In ion exchange process, it can be used. Zeolites. Sodium permutate process will be there. Removal of hardness. Next, natural ion exchanger is natrolite. That can exchange hot water ions. Next, ZSM5 is one type of zeolite. It can be used to convert alcohol directly into gasoline. Gasoline is nothing but petrol. Next here, see here it is given. Hydrated zeolites are used as ion exchangers in softening of hot water. Sodium permutate can be used. Na2, Al2, Si2, O8, XH2O. That can be used. Na2, Al2, Si2, O8, XH2O. So this is one type of zeolite, or it will be known as permutate. It is used in softening of hard water. Sodium aluminosilicates. XH2 means hydrated. This is best example for zeolite. Next, this is the end of synopsis of group 13 and group 14. In next video, I will explain worksheet questions of group 13 and group 14. All the best and thank you.